Hi, the title of my vision talk is Uncovering the Useful Structures of Complex Networks in a Socially Rich and Dynamic Environment. My name is Jie Wu from Temple University. Complex network has been used widely nowadays in many fields, including internet, food net, metabolic networks, and social networks. It is socially rich and dynamic. Today we'll talk about three challenges associated with a complex network. The first one is a graph model. The second is uncovering a useful structure in a graph model. Then the distributed and localized solutions. So when I talk about each challenge, I want to relate work in four different communities: graph theory, distributed systems, distributed computing, and social networks. Traditional graph is not sufficient to represent the dynamics of complex networks. So what is the right graph model for representing a complex network? There are a lot of work being done in this area. One special type of graph is called intersection graph, such as unit disk graph for MANET. Today I'll talk about another type of intersection graph called interval graph. The diagram shows an interval graph where each node represented by a horizontal line. The connection of nodes are represented by the intersection vertically. In that example, AC are connected. So there are several challenges. One possible extension is using hyperedge. In the above example, ACD are connected along a particular time instant. So we can use one edge to represent the connection among ACD. In this way, we can create a special type of a hypergraph called interval hypergraph. And in social online networks, person can be online multiple times. So we can have a multiple interval graph. Another type of graph representation is used to represent time, so-called time evolving graph. So the diagram shows a dynamic networks with a static node A and then several dynamic mobile nodes moving as circles. B and C as circles of 3 units, D is 2 units. So their connections are represented by a graph to the right, where the label along each edge represent the connection time. For example, A, B are connected at time 1, 4, and 7. So then there will be a lot of interesting new concepts. For example, the traditional path become a journey, which is path over time. So in the example, ABC is a journey if we select the link AB with a time 1, then B is a time 2 or 5. So those links should be non-decreasing in terms of number. Then diameter becomes the dynamic diameter, which represents the flooding time of a network starting from a particular source. Then the traditional shortest path can be an earliest completion time, which represents the time, the earliest time that a message can reach a destination, or the fastest path, which is a minimum span or minimum hop path. There's several challenges. One is the granularity. So we can represent time at a micro level, which shows the detail as in the time evolving graph, or the macro level, which is represent a high level, for example, probabilistic contact, edge Markovian models. Now we move to the second subject, how to uncovering useful structure in a complex network. We discuss the 3 methods. One is a structure training. So the idea is to train useless nodes and links in dynamic networks. So this is being used in the social network. So for example, how we eliminate certain neighbor, which are friends, while still connected, stay connected in the network. So this concept is being studied under the context of connected dominating set. There are many challenges. One challenge is in a dynamic training in the evolving graph with a probabilistic content. So one interesting example is a multi-bus riding example. So imagine a passenger is waiting at the bus stop and try to decide which bus to get on. And the bus arrival rate is probabilistic. So your objective is to try to reach a destination through with a minimum time. Then we can introduce a concept called the forwarding set. So just imagine the example of a multiple bus with multiple bus coming in. So your challenge is to select a subset of bus. So this subset called the forwarding set. So when the bus comes, it will decide whether you should hop on this bus or wait for the next bus. So how to optimally decide a forwarding set? So that's one of the challenge. And it depends. If the message utility is time sensitive, then the forwarding set is time varying. If you have multiple messages to the destination, then the forwarding set is copy varying, whether this is first copy of the message or second copy. So there's still lots of open research issue in this, deciding what's the best way to deciding the forwarding set. The second challenges relate to structure laying. So one example is the small world. So we all know that the world is connected through small world structure. So how can we discover other useful structure? So one example shows recently is based on the scale free. So scale free is a no degree distribution followed power law. And we found out that in several applications, including Nutella, it satisfies not just only the scale free, but nested scale free. So by nested scale free means that it's a scale free hierarchy done by peeling off lowest node degree. So basically it's a network in the diagram. By taking off all the lowest degree nodes, the remaining node, the subgraph, is still a scale free. And it's similar to the original graph. So by recursively peeling off this lowest node degree, so you create a set of nested scale-free subnets. We show an example what's the use of this property. Another way to uncovering structure is called a structural remapping. So the first example is a remap through the different representation. And a classic example is geometric routing. So the left diagram shows a greedy type of geometric routing. Suppose you want to route a message from the left corner to the up right corner. So if you do a greedy approach, you may stuck in the middle. You can imagine this hole like a lake. So you can stuck in the local minimum. So one way to do it is to do a new representation through mapping. So this is called conforming mapping using Ricci flow. So you can see that the diagram of left towards right. Then in this case, in the new diagram with a new virtual coordinate map, any message will not be stuck at the local minimum. So this type of mapping is called Euclidean space to non-Euclidean space in geometric routing. Now the question is, can we remap a problem not just in terms of representation, but from one domain to another domain? So one classic example in electrical engineering is FFT. But I want to show you another example. It's called structure remapping through mapping different domain. So one challenge is in the mobile network routing, like a DTM, is that the mobility is highly unstructured. So we have an unstructured mobile contact space in DTM. Now we try to map to another domain, which is static and structured. So this space we call the feature space. So imagine there is a person. Each person is represented by a set of features. So in this diagram shows like a gender, occupation, and nationality. Through one of the similar trace from Infocom, it showed that people with a similar feature tend to interact more frequent. So the diagram, the left bar corresponds to persons with one feature difference. Two means white one is a two feature differences. You can see the contact frequencies changes dramatically. So in this way, then we can generate a space called a hypercube space, where each dimension corresponds one feature. Then we set up the connections. So if two nodes differ by one feature, then there is a direct connection. So in this way, then we create a structured feature space. And this can facilitate efficient multipath routing when you try to find a destination. So this kind of the feature space give rise another challenges is how can we uncover the inference that social relationship on the structure of underlying network. You can imagine that in a multi-layer networks, you have a logical connection and physical connection. So how they interact, influence each other. So that's the challenges in this so-called multi-scale or multi-layer complex networks. So the third one, which is the final topic, is that once we have this connection, how we find this algorithmically. So we look at several solutions. The first one is called the static label. We mentioned earlier about the nested scale-free structure. By static label, it means each node is a label a small number of times. So there will be lots of work being done in this clustering, maximum independent sets, and connected dominating set. So just see this example in the diagram. If we label purely based on node degree, which is scale-free, so you can see that label 1 means the lowest rank in terms of node degree, then label 2, then label 3. Label 2 because this node has only 3 neighbors. Label 3 is because it has 4 neighbors. But if we use the nested scale-free, so we still have 6 nodes with label 1. Then we remove those 6 nodes. Then they have 2 label 2 nodes, level 2. Then 1 level 3. So we show that through many traces that this nested scale-free tends to generate kind of a DAG structures with one root instead of multiple roots. So this can facilitate efficient routing, especially up-down type of routing. Another one is through dynamic label. By dynamic, we mean that each node are labeled a large number of times. There are many examples in networks and distributed systems. For example, Bellman-Ford algorithm, PageRank is recursive defined based on the neighbors' ranks. So one classic example is called link reversal. So this is being used in several managed applications. The idea is to maintain a destination-oriented DAG. Like the leftmost example with a DAG D is a destination, so we maintain a DAG. Right? So that means each node has a path towards the destination. So what happens if there's a link failure? For example, the link between A and D fails. Then A lost the last outgoing link. then we have to reverse the links of A to reconstruct the destination-oriented DAG. So the idea is link reversal is you change the height of each node. So suppose eventually the height is based on some kind of topologic sort order towards D. In the second diagram, so you raise the height of A just one above all the adjacent nodes, which is C and B. So the level becomes from 1 to 4. So the level change of A may cause another sink. Sink means that the nodes without outgoing link, in this case is B. Then we have to do recursively. So raise the level of B from 2 to 5 to figure 3. Then raise the level from C, level C from 3 to 6, right? And so on. And we have to change 8 again. So 8 has to be changed multiple times. Eventually, the last diagram, you get another destination-oriented DAG. So overall, it has been shown that there is no efficient algorithm to quickly find a new destination-oriented DAG. But this is a classic example of a dynamic label. So which is maintain a structure which is a DAG. So before we look at some of the challenges, let's just classify the solution into two types. Obviously, we know the centralized solution, but we also have a distributed solution. We all know that it's a node's interaction with others in a restricted vicinity, say within K-hop, maintain and propagate labels. Localized one is a special type of distributed solution without information propagation. So that means you decide those links locally or labels. So the challenge is how can we deal with the complexity of building a structure along with the change of topology, especially in the dynamic environment. And there have been a lot of work done in the different fields. For example, in SDMs, they use a centralized one. For example, how to dynamically change the paths. Or in the mainnet, which is more challenges using distributed solution. So the main challenge is how you keep a view consistently, because each node sees different pictures of the whole network. Another challenge is how do we handle the long convergence time usually occurred in the dynamic label in a distributed solution. So let's look at some possible solution. So one way is that we can use some kind of hybrid of distributed and localized solution. And here is an example of fault-tolerant routing and broadcasting in a special type of graph called hyperqueue. So a while ago, I proposed this so-called safety level. It's a special type of coded labels based on the hyperqueue structure. So the number associated with each node corresponds to the safety level of each node. So suppose a node safety level is 1, it means that from this node you can reach any nodes within one hop through an optimal path or shortest path. If a label is 4, so in this case in a 4-dimensional hyperqueue, then that means it's completely safe. This node can reach any node through shortest path. So the question is, how can you quickly come up with this label? So it turned out there is efficient solution using only log n steps, where n is the total number of nodes in the hyperqueue. And this safety level decision is decided only once. So that means it's unlike the traditional dynamic scheme, which involve multiple iterations. Right? Obviously, the limitation is that only apply to hyperqueue. So as a conclusion, I discussed 3 issues related to complex networks. One is how we can come up a good model for a graph model for complex network. We look at the intersection graph, in particular interval graph for online social networks, and time evolving graph, which shows the time, discrete times. Then we look at 3 ways to build useful structures in a complex network through trimming, layering, and remapping. Finally, we discussed some challenges in designing distributed localized solutions using static and dynamic label, and one discussion on the hybrid distributed localized solutions. Thank you for